Thanks very much indeed to Rodney and John on the committee for the invitation to come and speak to Friends of Imperial tonight. John said, I'm going to talk about the need to address climate change and what we do of our energy systems looking forward at least to the middle of this century, if not into the second half towards 2100, which seems an awful long time away, but in terms of the problem that we're going to talk about tonight, it's not very long. The subtext, as again John alluded to, was having spent 20 years in the oil and gas industry, oil and gas very close to my heart, and the assumption is to deal with climate change that we have to get rid of fossil fuels and change to renewables and nuclear straight away. Well, we can't do it straight away. We should certainly do it as rapidly as we could. And so what I'm not proposing is that we continue to use oil and gas where there are alternatives. But my thesis is that it will take us an awful long time to reduce our dependency on oil and gas. So why are fossil fuels key to achieving a sustainable energy future? What can we do to live with fossil fuels but still address the issues of climate change? So to talk about this, I'm going to first of all talk about the energy landscape in general. What are our options? And I'm going to talk about the transition from where we are now, where we're still very much dominated by fossil fuels, to where we need to be later in this century. And I'll address this issue of fossil fuels, which is always the elephant in the room when we're talking about climate change. And I'm going to talk about, the title of the talk is Managing the Transition. I'm going to talk about how we manage the elephant. I will talk a little bit about, John referred to research I do in this area, and I'll give you a flavour of the nature of that research. And then I want to end up by talking about, given that we're going to manage this journey, how are we going to engineer our way from where we are to the future? And what do we need to do in technical terms, and what do we need to do in other terms? A lot of the blocks to implementation of technology are nothing to do with the failure of the technology. They're to do with other factors like the world we live in and people's attitudes and where the money comes from and things like that. And then I just want to end with a few challenges. What can you do to help manage this transition? So, what's the energy landscape? Who are the contenders in the energy space? On the left-hand side, in the red corner, if you like, we have fossil fuels. And we have the usual candidates of oil, gas, coal. But more recently, those are the conventional hydrocarbons. More recently, most of you, I'm sure, if not all of you, will have heard of shale gas with the controversy in the media and politically about being able to get unconventional gas in reserves that are far less permeable and more difficult to get out, shales, but the huge gas reserves there. And this has transformed the landscape in the United States and has the potential to do so both here and elsewhere. And there are other unconventional hydrocarbons. There are tar sands, a bit like the tar that we put on roads, exactly what we put on roads. So it's a very heavy hydrocarbon, almost solid-like, more nearer to coal. And as well as finding gas in shales, you can find oil as well. So there's plenty of hydrocarbon around, and I don't think shortage of hydrocarbon is going to be a problem. Gas is increasingly favoured. The great thing about gas is that it emits about half as much CO2 as all other fossil fuels, being CH4, whereas most other fossil fuels are roughly CH2 or below, higher carbon content than CH2. So gas, although it does not solve the climate change problem, a transition to gas means that you need to collect 50% CO2 per unit of energy compared with if you're using oil or coal. And the gas hydrates are very interesting. I do some research on that myself. They're ice-like structures that contain gas either in the permafrost or in shallow sediments that contain more gas than all the rest of the hydrocarbon reserves put together. The problem is that they're very difficult to get out, particularly because they act as the glue that keeps the sediment in place. And so if you've got subsea sediments and you try to produce the hydrates without thinking about it, you create tsunamis. So it's high risk, high reward. But it's another example of the fact there's no shortage of gas in the world either. It's just going to be more expensive and take more inventiveness to get it out of the ground. Then in the middle here we've got nuclear. Fission, been with us for a long time, and we've got conventional reactors, but now we have advanced reactors, pebble bed reactors and high temperature reactors that are modular reactors that are really transforming the nuclear industry, and so there will be more nuclear activity based around these new technologies. One problem with nuclear is, compared with a lot of other things, is the time to construction. The time period, it takes a decade almost to put a nuclear plant on stream. And so you need to have thought about this well ahead. It needs good energy strategy, which is something that a lot of countries are not noted for. And then there's fusion, of course. Nuclear fusion is probably 35 years away. It's always been 35 years away. And you'll note a hint of scepticism there. There have been advances, and maybe these are scalable, but if fusion does reach a breakthrough at scale, then of course that would have a very disruptive effect in our energy provision. Then there's the renewables, which are seen as the saviour of the planet. Don't emit carbon when they're used, and we have biofeedstocks, and that's carbon neutral because they're formed from CO2 from the atmosphere by photosynthesis, and then we release the CO2 again. There's other forms of biomaterials, bio-waste. We have hydroelectric, used in several countries, very geographically dependent, of course, and this is another point I want to make, that a lot of the solutions we're looking at are very dependent on geography and natural resources and will be possible in some countries and not in others. Wind, we have a lot of wind, and we've increasingly invested in wind in this country. Wave, tidal, so a lot of water-based potential sources of energy. And tidal's been in the news recently. I'll say a bit more about that in a minute. Think about all these sources, of course, they're intermittent. We only get electricity when the wind blows from wind turbines. We only get solar when the sun's shining. And so in this country, wind might be good in the winter and solar so-so in the summer. But we haven't solved the problem at scale yet of these intermittent sources of being able to use the energy when we want to rather than when it's produced. And so the intermittency and the associated problem of being able to store energy at large scale, grid scale, is, I think, one of the major blocks to fully exploiting renewables, and something which is a major area for development. We're very good with devices like these at energy storage. We may complain about the battery lifetimes, but on the whole, they're getting better and we live with them. So energy storage at the device level has transformed the way we live. I think energy storage at the grid scale will transform the way that we use energy. There's geothermal, the energy deep into the core of the Earth that, again, in some parts of the world is being exploited. And then, of course, there's solar. And solar, two major sorts: thermal, where we capture the sun's rays as heat and convert that into energy. And there's photovoltaics, where we directly convert the photons from the sun into electrons, and or we can go via chemicals on the way. So the potential of solar, of course, is enormous, but yet to be fully realised. And I've summarised all that on this, my version here of the energy landscape, which tries to capture those elements I've just described. The total world energy consumption about 15 terawatts per annum, and we see right at the centre there of fossil fuels, and well over 80% of our energy comes from fossil fuels. The potential is at least double what it is now, and from what I've said earlier, it's probably far more than that. But then if you look at the other options, what I've put on there is the existent and the potential, and you'll see that most of these are at the few terawatt scale, and they're limited in capacity to some extent, so that if we take biofuels, for instance, there will be limitations on the amount of land mass we can use to either for energy crops or for if we're going to use waste material from food crops. Wind, again, there are limitations that will be there in terms of certainly for onshore wind. Offshore wind, there's the oceans are vast, but the same limitations on capital investment as you have on offshore oil and gas. And some of the others are hydroelectric, geothermal, are very geographically dependent, and so are not universal solutions. So the message of this slide is that apart from solar in the bottom left-hand corner there, if we're going to get away from fossil fuels, there's no single bullet that's going to solve the problem. We've got to have a portfolio of renewable and nuclear energy to help in this transition. Maybe solar will be the ultimate. If we look there, that even if we just look at the radiation on land, there's potentially 30,000 terawatts. And so that's an enormous resource. Currently, the efficiency of converting that, particularly with photovoltaics, is still quite low, and so the cost-benefit of that and the scalability is still being looked at, although solar is expanding rapidly. But, of course, it's starting from a very low base in terms of the volume of energy provision across the world. So we have this fossil fuels right at the middle, which dominates, and we're trying to migrate to this broader portfolio, and so every country will have a different mix, and some countries are still just using fossil fuels because that's their most valuable natural resource. And so we hear concerned about the amount of coal in China and India, and they, of course, are going to exploit those coal resources unless there is a cheaper alternative, and we're not going to be able to, I think, prevent an awful lot of use of coal in those countries and elsewhere. Just mentioning the tidal wave ocean currents there, I think it's very interesting, the Swansea Tidal Lagoon project that has been in the news over this last week. I mean, the tremendous potential of us at an island, where on some of our, we have very high tidal height differences. I mean, it's something like 9 to 11 metres on the west coast of the UK, and Swansea is trying to exploit this with this barrier of about 9 kilometres long of Swansea Harbour there, where in that barrier will be embedded these turbines that you see in the bottom left and right there that are about 20 metres in diameter. And 4 times a day, when the tide goes in and out, then we can make use of this great potential energy of the tide to generate electricity. And so this project is of order 300 megawatts and will produce electricity for about 150,000, 200,000 homes. And it's a pilot project to actually see how this can be deployed where the tides are sufficient height to be able to exploit. And I think this is the first commercial tidal lagoon for electricity generation in the world. It'll be interesting to see how that goes and what the potential for expansion is. So there are some areas where I think the UK has been very innovative about its resources for energy. So the driver, of course, to move from this fossil fuel-centric energy system to a broader portfolio of renewables and nuclear, whatever we can lay our hands on that doesn't produce greenhouse gases, is this inexorable rise since the 1800s of the levels of CO2 and other greenhouse gas emissions in the atmosphere, which we see on the right there. Now well over 30 gigatons of CO2 per annum. And that graph, incidentally, it's only to do with power CO2. It doesn't include the CO2 from industrial processes like cement manufacture, iron and steel, which is a considerable generator of CO2 as well. And the consequences on the left there are that over that time scale we've seen the drift upwards of mean global temperatures and the relation of that to the increase of CO2 levels in the atmosphere from well below 300 to approaching and going through 400 as we've gone through the millennium. And I'm not going to give a talk tonight on climate change and the causal effects. I'm going to take that as read. There's plenty of evidence out there that anthropogenic climate change is proven and that we need to worry about the level of CO2 and other greenhouse gases in the atmosphere. Just a couple of interludes here. I'm going to show, first of all, how a bit more interesting than that graph I've shown of the increase of CO2 levels is how did that start? And if we go back to the Industrial Revolution, how did that spread? So this video just shows how CO2 emissions have grown, and it's a 1-minute version that takes us through from the 1700s to the present day. So you can see, first of all, there that in Great Britain, we're down in the blue is fairly low CO2, and as it goes yellow and red, then you need to get more and more worried up in the high hundreds of parts per million in the atmosphere. And you can see it spreading into Europe in the mid-19th century, and we're starting to get orange and yellow in Europe and the UK, and the United States building up, particularly on the East Coast there, very high levels as we get into the beginning of the 20th century. And they are spreading across Europe into Asia. And now you can start to see the explosion post-Second World War in China. And you can see that most of this is in the Northern Hemisphere. And there's some down in Australia there. But so if we expect China and India and Africa to not use the same route that we did for our industrial fueling in the 18th and 19th centuries, then I think we're being naive. And of course, this is all part of the... we'll get rid of the advert, I think. So that shows how things that started very, very small rapidly accelerated until it was a global problem. I've got quite a few videos here that are available on YouTube that you might want to, and I'll make the URLs, although available you can find them, I'm sure. The next one, which I'll just play a little bit of, shows you some modelling done by NASA of how the CO2 migrates into the atmosphere and how it varies according to the seasons. It's not constant, and it's not just a cloud of CO2 there that stays. It migrates with the atmospheric wind systems and so on. But it's very interesting, I think, to see. sound's obviously distorted, so I will talk over it. But this is just showing that red and purple are high levels of CO2, and in the winter months they're at their highest, and then as we go into spring and summer, as photosynthesis has a major effect, then the levels drop somewhat. But don't be fooled, they only drop between something like 370 and 390 parts per million, which are still well above the thresholds we need to worry about. But this is just showing the seasonal variations and the fact that the CO2 is moving about at different altitudes. What is it that we need to worry about in terms of changing our energy systems and responding to demand? Well, the other factor, of course, is that this is not a static system. It's a moving goalpost, that there are major drivers that are going to increase the energy demand in the future. The world population, currently over 7 billion, is going to rise so that by 2030 it's going to be probably over 8 billion, and by 2050, depending on which model you have, it's either going to be 9 or 10 billion. And so population growth, combined with the other factor that the major economic expansion is going to be of the BRIC and non-OECD countries outside the OECD and the developed Western economies, means that there's going to be an increasing thirst for energy of the number of people and the quality of life in countries that are developing their own systems. So the estimates are that world energy demand is going to increase by at least a factor of 2 by the middle of this century. So not only have we got to actually cope with the fact that we've got to, even with today's energy demand, we're not servicing that with non-carbon based energy. That's going to double in the next 30, 40 years. And so we've actually got to find systems that are robust enough to cope with that. And if we look at the emission scenarios with CO2, on this plot, this looks at the amount of carbon on the left-hand side. If you want the amount of CO2, you multiply roughly by 4 to get the amount of CO2. That the top line shows what happens if we just carry on as normal. So that's business as usual. We don't worry about cutting down on fossil fuels. We use coal, oil and gas wherever we have it. And we will use renewables where it's convenient and nuclear where the politics is right. And rapidly we'll reach 1,000 parts per million in the atmosphere. In 2000, CO2 was about 370 parts per million. In May 2013, it stormed through 400 parts per million and is still increasing. If you take the green line at the bottom, that's a 450 parts per million scenario. That's the one that was taken as the baseline target at COP21 climate change talks in Paris in 2015. And that will, if we're lucky, give us a mean global temperature increase of about 2 degrees. The 1,000 parts per million will give 4 to 6 degrees, and the consequences of that in terms of the creation of deserts, the melting of the ice caps, the rise of sea levels, and the consequences for human and animal life and agriculture are going to be really quite catastrophic. And that's where, if in the abstracts of this talk you've seen the word catastrophic, that's the sort of thing that we need to avoid. 550 parts per million, which some people think is about the best we can do with the best will in the world, still gives 3 to 4 degrees mean temperature rise. I'm an optimist. I think we can still achieve the targets that were set in Paris. 1.5 degrees is probably, it's good to have a challenging target like that, but if we can do 2 or over 2, that would, I think, still mean that we could mitigate the effects of climate change as well as avoiding a lot of the catastrophic consequences. So I think we should regard the green line there as the one that we should aim for. And given that we're over 400 parts per billion now, that's one indicator, which is one of the messages of my talk, is that time is running out. This is not something that we think we've got the rest of the century to sort out. We may not come to a final steady-state solution until later in the century, but we've only got a few decades to actually turn the ship round so that we're on course for capping CO2 levels in the atmosphere at the levels that we need to. And if you look at some of the scenarios about where we're going, this is a typical one, a global energy mix only going as far as 2030, but they're quite similar if you go to 2050, that shows the bottom 3 bars there of coal, oil and gas are still more than 50% of our energy mix by 2030, and they will be the same in 2050, with relatively small amounts of hydro and nuclear and biomass. Now, these are scenarios, and you shouldn't believe everything you see in scenarios because there's loads of assumptions in them. But I think the general message here that we shall still need to use to meet energy demand, because we can't meet it all with renewables and nuclear, more than 50% of that by the middle of this century, I think, is common to most of the scenarios. Interestingly, the dotted line at the top there shows the effects of using less energy. That blip there was the global recession in 2008, and the dotted line is how things would have continued if there hadn't been economic constraints on people pulling back on using energy there. So I think that, we have evidence that where there is a will to do things, it can be done. And using less energy, I'll come onto that in a minute, we can reduce our CO2 emissions by 50% of what they are now simply by using less energy and being more energy efficient. And this is the low-lying fruit that we're not actually doing enough about. Here, there was a very strong financial driver that was not intentional, and that shows what happens when you have one economic incentive there. And another problem I think we have with energy systems is that there are potentially economic drivers in terms of putting a tax on carbon or a charge on carbon that makes it more expensive to release it than just not to release it. Again, we only have a few parts of the world where we have those economic incentives to use less carbon. And this dotted line, I think, shows you how powerful economic incentives are. And they may be the major one we have to turn to. So why do I say that it's going to be very difficult on these timescales to bring renewables on stream fast enough and in volume enough? Well, first of all, there's the slow rate of developing technology and improving the efficiency of these systems. There are photovoltaics that are up in the 20-30% efficiency in the lab, but converting those to scale, it takes decades to get technology out into commercial scale. And so even though we may have embryonic systems in research and development, it's going to be a long while before we can bring those through. And combined with that, we've got to bring the cost down so that without subsidies, renewables are comparable with fossil fuels, but we've got to add the cost of capturing the carbon from the fossil fuels that I'll come on to in a minute to the fossil fuels to balance the equation. So we've got to actually compare like with like and make sure that there are economic drivers for the renewables to come through. There's availability. I've talked about land mass limitations for biomass particularly, but also for solar and wind. And I've mentioned the major problem of intermittency, which I think is the holy grail in terms of what we need for long-term intermittent energy. Nuclear has its own problems of safety, disposal, particularly of legacy waste and proliferation. And we know that that's a major political issue. Some countries that embrace it, like France, 70-80% nuclear. If you look at their carbon footprint, it's significantly lower than the rest of the European countries because they made that choice. Germany next door made the opposite choice following the Fukushima accident. And the consequences of an accident like Fukushima, of course, are decadal in terms of actually turning perceptions. And engineers have got a big role to play, I think, to prove the safety and viability of future nuclear. I just want to illustrate this development cycle of new technology. This is a typical S-shaped curve for the maturity of the technology compared with where we want to be in 2050 for biomass to fuels and biomass for power and heat. And there are 4 generations there of biofuels. I won't go into the details of them, but the one that's most mature at the top first is fermentation routes to produce alcohols and other fuels by natural routes, transesterification processes to convert plants to diesel. And these are mature, but they're not. They do compete a lot with food crops, and there's a lot of contentious issues about, particularly in the States, there have been issues about alcohol from wheat and so on. The second generation we're using the lignocellulose, non-edible, either waste from crops or using fuel crops, where we use thermochemical methods to convert them into chemicals and diesel. The third generation, where we take bioalgae and we squeeze the bio oil out of those, that's a very renewable route, and algae are very good at reproducing quickly. But again, that's very early days, and scaling that up is difficult. And the fourth level there is where we actually go all the way from, we use either synthetic photocatalysts or bioalgae to convert sunlight, use sunlight to convert things like CO2 and water to useful chemicals and fuels. And so there are these generations that are going to take decades to work their way through. I've just pointed out there that if we take biomass and we capture the CO2 from that, because the CO2 has come from photosynthesis in the first place, or used in photosynthesis to produce the biomass, if we capture the CO2, then we are in fact extracting CO2 from the atmosphere. And I think that's probably the most effective way to go carbon negative, as it's termed, to take CO2 out of the atmosphere. The other thing we can do is we can actually use biomass to convert this into plastics, which have a very long lifetime, and so we trap the CO2 in materials that are not going to degrade. Another example from the renewables area is this solar PV roadmap, which shows, this is produced by the industry itself, and shows the share of global electricity in percentage terms, and the projections to 2050. And so the industry itself is projecting that no more than 10, or maybe, if one puts error bars on this, 15% of PV can contribute to the total global energy system by 2030. And so this is, again, despite the fact that it's a very accelerating contribution to energy, the rate at which you can contribute to this massive and increasing energy target across the world is going to be later into the nearer the middle of this century. So I've put more of the renewables on this curve just to show you that whilst we've got some that are relatively mature, we've got an awful lot of the things that we're putting our hopes on that are in the relatively early stages of development, and it's going to take us well into the middle of this century to actually commercialise them at the appropriate cost and volume. So what are we going to do? This is another version of the CO2 emissions curve. This has got the number of gigatons per annum of CO2 emitted against time going out to 2050. And the top of this graph is the business as usual 1,000 parts per million curve that I had as my red curve. And the bottom is the 400 parts per million curve that is our target to try and achieve roughly 2 degrees mean temperature rise to cap that. And then in between, there's different colours that show how much carbon you could take out of the system using different approaches. And if you take the bottom blue and yellow, those correspond to essentially using less energy, energy efficiency, and fuel switching from coal to gas so that we reduce CO2 that way. And so 50% of the CO2 that we need to take out can be done by these energy efficiency measures, which are simply being better, more efficient at using energy. So this involves making our processes more efficient, but it requires individuals and governments to take decisions about using less energy and actually thinking about it in a way that we perhaps don't now. If you look at the difference between the top of the red curve at the top and the bottom of the blue curve, it's roughly 50 gigatons difference between the 62 and the 14 gigatons there. So by 2050, we've got to take out every year 50 gigatons of carbon dioxide, stop it being emitted to the atmosphere, compared with if we did nothing at all. So of that 50, we've got to 25 gigatons per annum can be taken out by energy efficiency methods. The next two bars show that with renewables and nuclear, 30% of that, so another 15 gigatons can be taken out using renewables and nuclear by 2050. And that may vary, of course, because these are scenarios. But that still leaves another 20% that we can't achieve either by energy efficiency or going to carbon-free sources of fuel, which means that it's back to my original thesis that we'll need to continue to use fossil fuels to meet the rising energy demand or even the existing energy demand for well into the middle, if not beyond, in this century. And the only way that we can do that is to actually take out the CO2 when we're using the fossil fuels to produce energy or use it for heating or using it to produce chemicals, wherever that's done centrally to capture the CO2 from the flue gases that are emitted and then to store it in the subsurface, either in depleted oil and gas reservoirs, depleted coal seams, or in deep saline aquifers, and then to store it there for hundreds and hundreds of years so that it's not released into the atmosphere and it's secure. And if you look at how much that is, it's 20% of this 50 gigatons, so it's 10 gigatons of CO2 a year has got to be actually taken out of the system by carbon capture and storage. So you haven't got to remove all the CO2 by carbon capture and storage, you've just got to remove that 10 gigatons per annum. And we'll see whether that's a challenge or not in a minute. So there's no way we can continue to use fossil fuels on the timescales I'm talking about without taking the carbon out of the system. The way that carbon capture and storage works, I'm sure most of you will have heard of it or may even know some of the details of it. Basically what you do is you capture the CO2 from the gas streams emitted from power stations and industrial plant with absorption in liquids or absorption on solids, and then you need to extract it from that and then transport it, ideally by pipeline. So we have a CO2 grid, just as we have a gas grid and an electricity grid now. And you take that to wherever you have these major sinks, typically offshore in the UK and the North Sea, depleted oil and gas wells. And the people ask, well, is there enough space to store all the CO2 that we need to? Well, there's more than enough space to cope with this 10 gigatons per annum by 2050 across the world. One of the issues, of course, is where the sinks you want to put the CO2 are in relation to where you're generating the CO2 by the different processes and how you're going to transport it there. So in the early days, you might have to use tankers or containers before pipelines are put in place on the scale that we need them. But these figures show that there's no shortage of, there's currently potential storage capacity for over 2,000 gigatons of CO2, and that's, I think, a conservative figure. And there are How much has this been put into practice? Well, it's been used for demonstration projects for over 20 years now. The Norwegians were the first to try this in the North Sea in their Sleipner project. And why did they do this? Well, surprise, surprise, the Norwegian government were one of the first to put in place a carbon tax. And so the incentive was that it's cheaper to store it under the North Sea. Their carbon tax was realistic, about $55 a tonne. That means that it's more cost-effective to store it than it is to pay the tax to release it. And there are various forms of charging for carbon, which I won't go into now, but it's a task that has avoided governments getting their mind around it and being willing to take the political consequences of introducing yet another tax to make our energy more expensive. There is one commercial project that was launched about 18 months ago, and that's in Saskatchewan in Canada. It's based on a coal-fired power station capturing the CO2 from the flue gas. About 1 million tonnes of CO2 are stored per annum, as in the Sleipner project in the North Sea. That's the equivalent of removing about 250,000 cars from the road. So these are making a significant impact. This is aided by the fact that you can use the CO2 for enhanced oil recovery on nearby reservoirs to get more oil and gas out of the ground. And that is one reason why this can be commercial, whereas other operations in the absence of a carbon tax or subsidies find it very difficult to be commercial. And so this map just shows that there's a lot of projects that have been tried across the world, but very few of them are at the scale of 1 million tonnes of CO2, which is what we need. So, there's controversy about CCS. Is it, as Greenpeace say, just simply an excuse to continue to use fossil fuels further? Or is it an inconvenient truth that we can't continue to sustain the quality of life that we have and the quality of life that the developing world needs without we actually continue to use fossil fuels? And the consequence of that, therefore, is we have to develop CCS at a commercial scale. And it's not only altruistic, there are real economic consequences. So this is a report issued by a cross-party committee of MPs, and I rather like the cover of the report I've reproduced there, because into the words electricity, they've managed to fit all the things about energy that we've been talking about, and storage is right at the top as the E of electricity. But this report shows that if we delay deploying CCS in the UK, then the costs to the nation by 2050 are of the order of 30 to 40 billion pounds. And the reason for that is at least twofold. One is that if you don't use fossil fuels with CCS, you have to deploy renewables whilst they're still very expensive, unless you subsidise them a lot. And therefore, the cost of electricity goes up by the premature deployment of renewables compared with CCS with fossil fuels. The other thing is that CCS, carbon dioxide is emitted, a lot of it, from industrial processes. And I mentioned a few: iron and steel, cement manufacture. It's a major business worldwide. Most of the things we're surrounded by in terms of construction, either plastics or cement and concrete, generate enormous amounts of CO2. And there is no other way than by capturing the CO2 that we can actually avoid that CO2 going into the atmosphere. So we need CCS for that reason as well, and the consequences of that. There's a comparable study in the US that showed that the cost of electricity in 2050 with and without CCS are factors of 2 or 3 different. And it is, I contend, probably the cheapest way to actually reduce carbon emissions in the short term. So we have this short-term view of CCS. What about the long term? Well, one thing that we're working on here, and could be a possibility, but it requires a paradigm shift. If we're going to continue to use fossil fuels for most of this century, as I believe we do, then the way we currently do them is very inefficient. We bring everything up to the surface, lose a lot of energy for that. We use a lot of energy to transform the oil and gas into things we want, generates more CO2. Then we capture the CO2 and then we pump it back down again. So why don't we, in fact, do a lot of this processing in the subsurface, and all we bring up to the surface is what we need, which is low-carbon fuels like hydrogen or methane, electricity and heat, and syngas, carbon monoxide and hydrogen, from which we can synthesize most of the chemicals and fuels we want, and we leave the heavy stuff, and we also leave the carbon dioxide in the subsurface. But that will take us several decades to perform. But if we're going to continue to use fossil fuels, I contend that what we do now is not the best way to get it out of the ground. So, how do we use fossil fuels more sustainably? The resources, first of all, let's address that issue. Well, I don't think we're going to run out of fossil fuels, even if we continue to use them till the second half of this century. And the cartoon character there is Fred Flintstone. And just as the Stone Age didn't end because we ran out of stone, the fossil fuel era will not end because we run out of fossil fuels. It will be because of other factors that economics, politics, regulation drives it in that direction. So what we've got to do is to eliminate CO2 and greenhouse gas emissions, particularly from central generation facilities, and engineer the environmental impact so that fossil fuels have a similar impact compared with renewables in terms of carbon release. And in the meantime, I think we can regard this as a low or zero carbon bridge to renewable energy. So it's not displacing new renewable energy. We should continue that as fast as we can. But it is buying us time that, unless we want to revert to an agricultural economy, that we have the time to actually make that transition. And this is why I think fossil fuels are so crucial, used in the right way, to enable us to make this transition. So, if you like, the nuance of... I posed a question at the beginning of how do we manage this transition. This slide, in a way, summarises my view of how we get there. First of all, we use less energy. And if possible, we use 50% less energy, and that's the low-lying fruit of the lemon tree, is it? I don't know what the fruit is. But the second thing is that, while we continue to use fossil fuels, we use more gas and less oil, and as little coal as we can, but we can make a decision not to use coal. We've closed down 3 coal-fired power stations last year in the UK, but the same is not true in other parts of the world, and we can't expect that to happen. So we've got to go to the third option there, is that we capture as much of the CO2 as possible. And if we use gas, we should take the CO2 from gas as well. Gas is not an excuse for not capturing the carbon. We need to take it from the gas as well as from coal and oil in petrochemical plants. We should increase nuclear. I believe that nuclear is a large role to play in the future, but it's not a fast option. And a lot of the technology, there are issues with proving the new technology as well. And we have that in this country as elsewhere. Meanwhile, with fossil fuels, we should actually mount the transition to a portfolio of renewable energies as soon as possible. But I hope I've indicated that this is going to take us 50 years at least, and it's going to be very country-specific, depending on natural resources and policies. So, for instance, New Zealand has 70-80% of its electricity from renewables. It has hydroelectric, it has other things that it uses. Australia, its neighbour, is almost the reverse in terms of fossil fuels, particularly coal. So this is going to be very specific, and energy strategy has got to be worked out on that basis. So my green point there is that I get very frustrated that having got the agreement globally at COP21 of this target, that there hasn't been any more progress on some international agreements on carbon pricing. because it's the sort of thing that it's very difficult for one part of the world to put a penalty on its goods and its trading by putting the additional costs on if the rest of the world is not going to. And so it does really need some universal accord about how we're going to meet this tremendously challenging target. So people were very happy about COP21. They said, we've cracked it. We've got agreement on 400 parts per million, 1.5 degrees centigrade, maybe 2. But for me, that's just the start of the story. The actual challenge is now how do you implement that? And countries can do what they can locally, but there are some things that does require much more international accord, and carbon pricing is one of them. And whilst the European carbon trading system has not been very effective, at least it exists. And that may be one of the unintended consequences of Brexit, that we're not part of that. We do have our own carbon floor price to add on top of the European trading system, but that's been capped till 2020 at, I think, £18 a tonne, which is nowhere near high enough to drive people to have to bury CO2 rather than release it. So I go back to my CO2 emissions plot, where we said, what are the ways that we can actually take CO2 out of the system? Just because 2050 is the target there, it doesn't mean that we've got decades to do this. The problem starts now. Unless we actually start to act now, then this will be a moving goalpost, and the amount that we need to take out by CCS, if we don't introduce renewables or do energy efficiency rapidly enough, will go up. And so it's absolutely critical that we make progress. Well, how are we doing on carbon emissions? Well, 1990, 2.39 tonnes of CO2 per tonne of oil equivalent energy used in the world. You look at 2010, 2.37. Within the noise, we hadn't made much progress. With the US using shale gas, there's been a period where atmospheric levels of CO2 have been increasing more slowly because of the increased use of gas, and that's encouraging. And it may be a foretaste of what are the benefits of actually using gas, not short term, but maybe longer term, as a way to keep things down. But I contend that in a non-CCS world, we haven't been very good, since we're still continuing to use fossil fuels at enormous levels. We're not stabilising the carbon emissions. There is a chink of light. These plots here show that if the one on the left is the total carbon emissions, and you can see in the last few years it's flattening out. And at the bottom there, we've got the global carbon emissions in tonnes of CO2 per tonne of oil equivalent. Whilst it's been going up over the last decade or so, 2015 was a significant year maybe, because the carbon emissions were 35.7 gigatons compared with 2014, where they were 35.9. Now, I know you can say this is in the noise, but unlike other times, this was where there was significant economic growth. And so this means that there's been a decrease of CO2 in real terms, whilst energy consumption has gone up. So that's encouraging. The other plot just shows the major CO2 emitters and how China has outstretched the United States over recent years. The EU is coming down, but India, the black line at the bottom, is going up. And so whilst there's a chink of light, there's a long way to go. And so coming back to CCS, can it solve the problem of taking out this 10 gigatons of carbon dioxide by 2050? Well, we currently have about 50 CCS projects worldwide, some of them demonstration, going from something like a few hundred kilotons per annum to a megaton, 1 million tons per annum. If we're to meet that target, then by 2050, we've got to put in 3,000 projects at the megaton scale. So you can imagine the rate that we need to put them into place, 100 projects a year after 2020 in order to meet that. And so whilst there are megaton projects that are now being carried out technically very effectively, I come back to the fact that until we have a carbon price that drives this, waiting for the market conditions is like fiddling while Rome burns. I just want to digress for a few moments just to say a few words about the UK. This is the energy demand forecast in 2013 that shows that even by 2030, whilst solids, coal at the bottom, are going to go down a lot, that oil and gas, the hatched grey and the green, will again be more than 50% of our total energy mix by 2030. I think nuclear will hopefully be more than it is there. But you see that renewables, although it's significant, it struggles to actually expand very quickly there. If you go to the 2015 projections from what was DEC and is now BASE, the new Department for Energy, the top shows that renewables and nuclear up to 2050 will increase to about 50 million tonnes of oil equivalent for energy. The coal in the middle will decrease significantly and almost become extinct, whereas oil and gas at the bottom, they're not going to increase, but they're going to remain fairly steady over this period at a level that's still significantly about double that of the renewables and nuclear. So all the UK government projections confirm this scenario. We will continue using oil and gas at least to the middle of this century, if not beyond. Now, there has been some encouraging news in terms of the face of our energy mix, in that if you look back at 2016, this was the first year where wind provided more electricity for us than coal. So wind was 11.5%, coal was 9%. 3 coal power stations were closed down, and gas has increased to 45% of our electricity mix. And you can see there on the graph at the bottom that, in fact, our total energy consumption is going down. So we are doing something about the energy efficiency and more efficient use of energy and less use of energy. And this is the carbon budgets that the UK has set itself. We're fairly unique in having a climate change act that embeds in law that we will actually reduce by 80% our carbon emission levels from 1990. You can see on the right there the target of 120 megatons of CO2 equivalent by 2050. And you can see the different staging posts of the budget. And the solid line is how we're doing. So far, so good. But if you actually look at how we're going to go from where we are now, certainly with the next carbon budget to 2050, then we've got to continue to use fossil fuels to meet our energy demand. With no CCS, we're not going to get there. And we did have a competition, 2013 to 15, 2 final contenders, the Peterhead project, there's a diagram of there, and the White Rose project that was going to put stuff into an aquifer in the North Sea from a coal-fired power station. Both these had been through the design stage and were approaching commissioning when the Chancellor removed the funding in his autumn statement in November 15. And so the UK is in a position where, having had 2 tries at a competition, we still haven't managed to get this technology to the level where it's semi-commercial. And however, one lives in hope. This is a project that some of you may have heard of. The latest idea is that we use 30% of our carbon emissions come from cooking and heating in domestic and commercial organisations. And there's a plan to actually use hydrogen for heating, and hydrogen can be generated from methane gas reforming, where you actually produce hydrogen and CO2, and you take the CO2 off and you store it. So if you're going to produce hydrogen from fossil fuels, you need carbon capture and storage to get rid of the CO2. You can produce it from electrolysis of water, but if you're not going to generate more CO2, you've got to use renewable electricity to do that. But So hydrogen is not the universal solution unless you think of how you're going to get it. But Northern Gas Networks, a gas provider in the north of England, with partners, has got this project where it's planning to use Leeds as the test bed for providing hydrogen for domestic heating. And to use the existing gas grid, all the appliances will have to be modified, but that's no different than what happened with going from town gas to natural gas 50 years ago. So we've been through the experience of what we need to do there. So it'd be very interesting to see that whether this actually does get sufficient funding to be carried out and leads to be the pilot as to whether hydrogen combined with the offshore there is where the carbon dioxide is being stored offshore. So I'm running out of time, so I'm not going to dwell too much, Chairman. I'm going to finish shortly. My own research crosses the energy landscape. I'm very passionate about making CCS work, and this Carbon Capture and Storage Centre, QCCSRC is its acronym, is understanding the fundamental science and engineering of the injection processes into sandstone and carbonate reservoirs, the ones in the Middle East, the ones in the North Sea, the ones in the Gulf of Mexico, at how we can optimise that process and ensure that the CO2 stays there more or less forever. I'm interested in how we continue to use fossil fuels, but going beyond CCS to how do we actually leave most of the waste in the ground and just produce the high-value stuff like hydrogen and methane. And I also do some work on using cyanobacteria and green algae, which are very good photocatalysts, to convert water into hydrogen using sunlight. Currently, we produce a few litres a day, so that's got some way to go to meet the demands of Leeds. But we do all this under the umbrella of the Imperial College Energy Futures Lab, which is an umbrella organisation, a one-stop shop for all the energy research we do, which has hundreds of researchers across different departments and institutes, and about 20 research networks that are shown there that look at different parts of the energy portfolio, all the way from oil and gas, carbon capture and storage, to photovoltaics and biofuels and wind and hybrid vehicles and so on. So the Carbon Storage Centre that I helped to found, that I was director of until a couple of years ago, is funded by Shell and another partner who also happened to, those of you in the football aficionados will recognise Lionel Messi, and he is sponsored Barcelona by Qatar Foundation, and they are one of our sponsors of this. So they have good taste. And this is a 10-year programme, $70 million, so it's unusual for an industrial university programme in that we have 10 years to actually do research, try it out in the field, see where you didn't do the right research or you got it wrong, and iterate round the loop with our partners. And we're very grateful to them for the trust they've shown in us in actually understanding, particularly carbonate reservoirs, the reservoirs you find in the Middle East. And so this slide just shows the variety of activity, the number of staff that have been involved so far. And we rather like our strapline, which is putting CO2 in its place. A lot of what we do uses imaging. So we use CAT scan imaging. This is a medical CAT scan that has been adapted to look at oil and gas and carbon dioxide in rocks. And we can also do it at the very small scale where we look at the pore size scale, which is of the order of microns, what's happening in the actual pores of the rock, rather than on a longer scale. And the way that CO2 is trapped in the rock, the blue there is supercritical CO2. It's supercritical, very high, it's above its critical point, so it behaves both as a gas and a liquid, in that it's got the density of a liquid, but it's got the viscosity of a gas, so it's very easy to pump in there. And if you then flood it with water, you actually trap the CO2, as those globules show there. This was the first micro-CT observation of trapped CO2 in a rock about 10 years ago now that we did. And one needs to understand, what is it that keeps the CO2 there? Well, the thing that keeps the CO2 there is the interfacial tension between the CO2 and the surrounding brine or water. So you have a cap rock that provides your ultimate seal that's impermeable so it can't come out, but you have this capillary action that keeps it in there, and then over time the CO2 dissolves in the water or the brine and is denser and sinks to the bottom of the reservoir. So if you like, you have belt braces and suspenders as mechanisms for actually keeping the CO2 in there for centuries. And here are a couple of my PhD students who were studying these droplets of supercritical CO2 falling into the brine at high temperatures and pressures, and from the shape of those droplets they can deduce the interfacial tension, which then enables us to say, to predict more reliably how the CO2 is going to get trapped in these reservoirs. And I'll just show you this video, which is of a small core of carbonate rock, and we're going to move up and down the core. So as you see different images, it goes up and down, and so we're taking a cross-section through the different pores of the rock, and you'll see the different fluids. The dark colour is the CO2, the light colour is the brine, but we'll go into colour in a minute, and you'll be able to see that. And so this is just showing that the white are the rock particles, you've got these pores in between, and you've got a dark fluid, which is CO2, and a light fluid, which is the brine. Now, the orange now is the rock, and the blue was the CO2. And what we've now done is we've stripped away all the rock. So this is just the CO2 that is trapped in those pores, and the different colours just show how many pores are connected. Some are single pores, and you can see long ganglia that are connected. And now we're going to focus on a single drop of CO2. And you can see that this has flats on it, and that's where it touches the rock. And so this is a 3D image rather than the 2D image you saw before. And what we're now doing is if we move up and down, we can see that droplet is surrounded by blue brine, and it's trapped there by these capillary forces. And what we're going to do now is to do, one of the students in the project devised these algorithms to actually find out where it was in contact with the rock, that's the yellow line, and then you do a construction where we're going to measure the angle between the fluid and the rock. And those of you that know about interface science will know that that's the contact angle, and we normally measure that in the lab at ambient pressure and ambient temperature. In this experiment there, which has now disappeared, hopefully you saw an angle at the end, we can actually do it at 150 degrees centigrade and 1,000 bars, which are the conditions in the rock. And so rather than needing to actually assume that things are the same as they are in the lab at ambient conditions, we can actually do it in situ. So that's just one example of where we're making measurements that then we can put into models to make these processes safer. And I should recognise a whole host of people who do all the work. I just talk about it. So I come to the end of my talk. I probably, even, although we started late, I've overshot my time. I will not say too much about my final section, which is about what do we do to get there, how are we going to go from the current energy landscape of 15 terawatts to the future energy landscape where solar is now at the middle, fossil fuels haven't disappeared, but everything else is still part of this portfolio. And the way we engineer that journey is, I think, not to leave it to governments, but I think engineers are the key, and I would say this, wouldn't I, as a chemical engineer, that chemical engineers are very important in this, but there are 3 stages. Planning the journey, given we've got all these options for energy, what are the different journeys across this landscape linking together different energies that are going to be the most cost-effective, the most carbon-effective, and produce the volumes of energy that we want. That's going to need some. We've got lots of solutions at the moment, but it's also going to provide some innovative technical solutions that enable us to accelerate that journey and to reduce the cost. And then the third thing is public engagement, both with the public and policymakers and government, to actually convince them, A, of the urgency, and B, of what the systems that we need to put together are to actually enable us to get down that journey. And I've some examples of some of the technical challenges engineers need to address that I won't go into. But the quality of life that we're trying to influence, we've got technical solutions in the middle, but unless we can actually influence policy frameworks, economic drivers and public attitudes, then we're in a space where we're just likely to stay there for a long time because we're not going to get a consensus. We've got to have some persuasive arguments that move us from there. And so I ask, how serious does the problem have to get before the engagement is sufficiently effective? We need to be better as scientists and engineers at communicating in the language of the policymakers and the regulators and the economists rather than of scientists and engineers. And my statement at the bottom is that we are sleepwalking into a catastrophic climate change future. And I think hope I've convinced you that the timescales are so critical that we are not moving on anything like the speed we need to address this. So I encourage everyone, whatever your situation, to speak out and to actually tell the world that some urgent action is needed to address climate change mitigation, and to recognise the fact there's no free lunch. This will cost us. And if we're looking for solutions that are cost neutral and don't actually mean that we have to pay for the environmental damage that we're preventing, then we and governments and people across the world are kidding themselves. And so I end up with, what can you do? So I hope you go away thinking, perhaps if you haven't thought about it before, to think a bit more about it, to engage in the energy debate. It's a very good dinner or pub conversation. You can play your part in energy efficiency. Try setting yourself the challenge of saving 80% of your 10 tonnes of CO2. I didn't emphasise that, did I, on that CO2 graph. Every one of us in this room, on average, in the UK, produces 10 tonnes of CO2 a year. Can we get that down to 2 by our lifestyle? There's a couple of calculators there that you can go to that enable you to actually calculate your own carbon footprint and to look at some of these scenarios about, if you say that you don't like fracking, but you do like solar and you do like biofuels, think about the fact that biofuels may be carbon much better as far as carbon's concerned, but it uses 100,000 times more water to produce a unit of energy than fossil fuels do. And so we've got to worry about water and food and health as well as energy in this future scenario. Encourage local projects, local initiatives for things like local heat systems and local power systems are very well worth pursuing. Those of you that are in the early stages of your life and career, consider a career in energy science and engineering. If you want to change the world, this is an area that desperately needs you. So persuade others and lead by example. Thanks for your attention. Thank you.